Okay. Welcome to Partial Differential Equations, to the honours class. What I'm going to do today is I'm just going to give you a bit of a course overview, how the logistics are going to work, and then give you an introduction to what PDEs are, how we go solving it, how it's different from ODEs, and start giving you the definitions, and then a few elementary examples. Okay, so all my stuff for the course can be found on that website. I think you've got the link already. And basically, this is my physical contact information. So, and I'm going to put office hours up. They're usually after every lecture, although I wanted to discuss that with you guys some more, but I'll do that if other people eventually arrive. Just to make sure that everybody actually has time to come and see me if they get stuck. But really, during the lecture, I actually encourage you to ask questions. Right? If there's not something you don't understand, slow me down immediately and ask it, so I can explain it. That worked best last year. I had a very nice class where there was one particular individual that asked so many questions I went really slow, but I think it actually sort of greatly increased the degree to which people understood. Okay, our lectures are today from 11 to 1, and tomorrow from 11 to 1. Okay, and this might change depending on what the other requirements are. Okay, and then for now, consultation after the lectures as, but that might also change just so that everybody, I just want to make sure that everybody can get hold of me. Okay, and the first thing is if you look on the website, you get this picture. So to me, ODEs is not just a course, it's something I'm actively involved in solving. Okay. So this picture is a picture of a grid that I'll tell you more about that I'm trying to use to solve two black holes colliding head-on. Okay, so it's basically a section of space-time with a certain set of coordinates on it. And it's just to give you a flavor of what we're going to do. As we come along, we're going to basically get the basics of ODEs, but then there are going to be very practical tricks that you learn along the way, sort of how you choose coordinates, sometimes the math will actually tell you what coordinate system is the best to work in. And this is an example of a separable coordinate system that we'll also get to later on. Okay, so the references I'm going to be using is mainly these lecture notes, actually. I've gone through a number of references and I'm going to list them there and sort of extracted the stuff I can fit in reasonably to a semester course at honours level. So, but this is where all the stuff comes from. This used to be the textbook they used in the past, Partial Differential Equations and Applied Mathematics. It costs between 4,000 and 6,000 Rand, which is why I didn't actually require it. But if you ever can get a second-hand copy, do. It's a useful reference. It's also found in the library. So if you are, I think there are like 2 or 3 copies in the library. So if you're quick, go and take it out and at least keep it for the semester, because it's a very useful reference and there are lots of problems and examples and stuff there in addition to the course. Another one is Partial Differential Equations for Scientists and Engineers. There's an ebook that you can get for $10 US, so that's a little bit more affordable, and it's online, so I didn't order it in the bookshop. It's very practical, and you'll see in the course website that as I go along, there's reading next to the side of the weeks, as well as the relevant chapters out of various of these books. So if you want augmenting material beyond just the lectures, which I actually strongly encourage you to at least go and look at it once or twice and see if it's useful to you. Okay, this is also a very good book. This is a slightly higher level. It's more the rigorous math, and I tend to steer a course between the rigorous results and practical applications as well. This is Evans. It's a very good book. This one I used to start. This is a very old book. It's a classic. It's Partial Differential Equations, 4th edition, Fritz John. There are online copies available, so I would download that. Especially the first part of our course comes directly out of that. The first order equations comes out of Fritz John, and he does a very good job of it, or sort of a condensed version of what he did. And then this is another more practical one where they do numerics and stuff. This course is mainly going to be the theory. But there are going to be one or two examples where a computer is useful. But this guy will actually, if you ever start modeling the partial differential equations, this is quite useful as well. And then finally, there is this textbook online that I actually used the first time because it was free. But then there are a couple of typos and mistakes in it, so be careful of that one. But there are useful things in there as well, so you can go and check out the link. And if you want things beyond just what this course has. Okay, so why do we study PDEs, right? Basically, most fundamental laws of physics, in fact, almost all, with the exception of a few theories, are physics, economics, engineering, are formulated in terms of PDEs. There are a few people that try and do things beyond formulating it in PDEs, but then they effectively use discrete systems like Wolfram, Alpha. Wolfram, he's one guy that doesn't. He wants his cellular automator rather than PDEs. But you can show in certain circumstances they are actually the same thing. There's a relationship between. So he's not even he is escaping PDE. Entirely. It's encountered in most forms of mathematical modeling. Examples are fluid dynamics, electricity, optics, heat flow, GR, feedback control. This is interesting. When they put satellites up and they want to correct the navigation system in real time, or where they shoot missiles, and you have these missiles that zone in and track, say, a hotspot or an engine. There's feedback control, and that's quite a difficult problem, but it's a very fun one, and PDE theory comes in there a lot. I've used this, or basically been with people that used this when we did the binary black hole simulations. We physically wanted to track the position of the black hole in the grid, and then you use feedback control there as well. So, and then, as I've said, satellite trajectories. Okay. Now, the reason why we study PDEs is the same equations result from many different contexts. So rather focusing on the one specific problem, you can have several problems that result in the same PDEs, and therefore if you learn to solve the techniques to solve those PDEs and get a feel for those PDEs, you can actually say something about several problems. And this is my preferred way of actually doing physics, is using the mathematics as a very rigorous guide for what is possible and not. So the properties and the solution method transcend application. And in fact, you can see when PDEs developed and classical mechanics developed, the two drove each other. And that's happened again throughout history, like general relativity and differential geometry. You had the two legs growing together. And more recently, string theory and some very abstract algebra results also were going together. So it's kind of a marriage between pure mathematical reasoning and applications that then inform the reasoning as well. Okay, because PDEs are hard. The ones we can solve exactly are few. However, what we learn from solving them in the general theory there actually changes the way we think about the world around us. And so I hope during this course you get some feel of that, right? Right, just one example of that is there are different types of PDEs. For example, PDEs that govern heat flow. Heat has certain properties that just like goes shoo and disappears. Whereas a PDE that governs like Laplace's equation, all it does is pull something tight. So it's dependent totally on the boundary. And then it pulls the thing tight in the middle. So there's nice little physical ideas that are associated with your PDE solutions. And that's so that the heat flow is an example of a parabolic, which we'll get to. The Laplace's equation is an example of an elliptic, and there's certain solution properties that we have. And another example is the wave equation, where you have waves that just go out and energy is conserved, and that's an example of a hyperbolic solution. So there are different types of PDEs that result in different types of properties of the solution, and those properties are visible in the world around us as we see them. And once you get to know them, you get to say very profound things and you see a problem, and you already start knowing what properties the solution could possibly have, and therefore how the physical system could behave. Okay, so some notation and definitions. Firstly, an ordinary differential equation is a function that depends on only one variable, f of t. PDEs, on the other hand, partial differential equations. The unknown function depends on several variables, so for example, x and t. So it's one step up from what we did in the third year, where we actually studied dynamical systems and ordinary differential equations. This now has several variables, and that's to be expected in many real-world circumstances. We very seldom have the luxury of having plain ODEs. Most of the things are functions of several variables, and though that doesn't mean to decry what we did the last year, because what you see we're going to happen is we basically, in some circumstances, are going to reduce the studying of PDEs to the solving of ODEs. Okay, so we're building on what happened previously and just getting stronger in describing what we can do. Okay, so just my notation, because I tend to mix it up, and the textbooks tend to use different notations depending on the preference of the person who wrote them. A first order ODE, or you basically have the first derivative with respect to t. I sometimes write it as simply just ut, but then you must remember that you're holding the other variable like x fixed. So this is simply, you can also write it as the partial derivative of u with respect to t, okay? Or you can also write it like this, where somebody told you beforehand that u is a function of x and t. Or people write it like that as well, okay? And this is just the other variable. So if u is a function of x and t, your first order derivative is the derivative with respect to t, the derivative with respect to u, and so you have the same variation notation. It's just du dx, and the second order derivatives of a function of several variables, in this case 2, you simply have uxx, so that's du dx squared, uxt, that's du dx, du dt, and the order here doesn't make a difference. Later when you do tensor analysis in the next semester, you'll start seeing that sometimes that's not true. But for all the cases we're looking at, if u is just an ordinary function, then this is so. You can just swap the order, and utt is the second derivative of u with respect to t. So, okay, so those are all the possible second order derivatives. And what we call it, we simply say u is the dependent variable because it depends on x and t, and x and t are the independent variables. So I'm just defining systematically everything so that when I get into the meat of stuff, it's easier to follow. Okay, so some of the very basic examples of PDEs is basically the simplest first order equation you can get is u of x is equals to 0. Okay? The next one is what we call the advection or the transport equation, where du dt plus c times du dx is also equals to 0. Another example that you've seen a lot is Laplace's equation. This is the equation that I said pulls tight. It tends to pull things tight. And Laplace's equation, if you know physics, you find it in around a static charge. You find it in the gravitational potential, and many other places. And it's associated with those things in physics, but it is also associated with complex analysis. Okay, so solutions to Laplace's equation in 2 dimensions. Solutions to Laplace's equation is they call harmonic or potential functions, and just in simply if you're solving Laplace's equation in R2. So here's also another important feature. Partial differential equations you can solve on different domains. You have some equations that have the same properties, whether they're in 1 dimension, 2 dimensions, 3 dimensions. And one of the classical examples is Laplace's equation. Laplace's equation is also actually no accident that it appears so often in physics. In fact, if you also do the tensor course the next year, you can actually argue it's the simplest possible equation you can make when you take 2 derivatives. Okay, so there's certain very powerful arguments for why Laplace's equation appears so often. So, and we're going to look at it also in quite a lot of detail later on. So, here's Laplace's equation in 2 dimensions. Here is exactly the same equation, but I've rewritten it in polar coordinates. So this is another feature that we're going to look at is Laplace's equation in Cartesian coordinates, Laplace's equation in polar coordinates. Even though the equation is different, the solution should be the same. Okay, it doesn't matter what coordinate system you solve the equation in, its properties is still the same. What typically happens is the solution depends on the boundary conditions. Okay, so you tend to pick a coordinate system so that your boundary conditions so that one coordinate is constant along the boundary. So if you're solving Laplace's equation on a box, a square box, you're going to use this. If you're solving it on a circle, you're going to use this version. But many of the properties you'll see are going to be the same. And that's what we'll derive later on. Laplace equations also exist in any dimension. So here it is in 3-dimensional Cartesian coordinates. And you can put it in polar or cylindrical and spherical coordinates as well. Same equations, same properties. Sometimes it is easier to solve in a coordinate system and you choose that. Okay, so this is still just giving you a very broad overview of what we're going to be covering in the course. Okay, so here's the heat equation. You can see the heat equation has one derivative with respect to time, a constant times the Laplace equation. So it's second order, in other words, 2 derivatives in the spatial components and the first derivative in time. It has certain properties. Another equation that you would have gotten that appears a lot in quantum mechanics is the Schrödinger equation. Look how similar they are. It's simply an imaginary part in front of the timed equation. So one way of viewing the Schrödinger equation is simply the complex diffusion of the probability sort of surface. And the solution techniques of these 2 equations are remarkably similar, and we're actually going to look at that as well. And in fact, the discovery of the Schrödinger equation, I've been reading this book about it, was very closely related to partial differential equations. And when you go deeper and deeper in, you have this combination between what people knew was possible, what the experiments were working at, and then how they tried to fiddle to get it to work. Now, the wave equation also appears very, very often. UTT, so second derivative in time, minus c squared, the Laplace equation of u. And let's just go back. And so that's also that's an example of a hyperbolic equation. And all these things have certain solution techniques that are common to them, as well as properties that are unique to the different types. So this is an example of a hyperbolic, this one's an example of a parabolic, and this one's an example of an elliptic equation. All these simplest equations are linear, so you can see there's u rather than u squared or something else there. And those are the ones we're going to study in detail as the course goes on. Okay, so another equation is the equation for an oscillating 1D rod or plate. Okay. Also it's not the wave equation, right? It's simply second derivative in time, and this is a Laplace equation squared. So there are going to be 4 derivatives with respect to x and y, right? It's simply this dxx squared plus dyy squared plus dzz squared squared. So it's a 4th order equation that's there. Okay, we're going to not look at that one so much, but there's certain things you can say about that as well. Here's another example of an equation. It's the equation for a minimal surface. So you know soap bubbles that you put in, you can have they're very remarkable results with the soap bubbles. In other words, their properties, and this goes into deeper than we're going to go. But if you if you wash the dishes for your mom and you agitate the water and you get a whole bunch of soap bubbles, those soap bubbles will only meet in 4 unique angles, like the walls of the soap bubbles. If you look at them carefully, there are only 4 angles that it meets, whether the soap bubbles touch each other or whether they touch the side of the basin. There's only 4 unique angles. And the guy who discovered this first was Plateau, who was a physicist.
Washing dishes.
He must have been washing dishes, but he actually studied soap bubbles a lot. He said he observed this, and people verified it, and it took a very long time to prove. And in fact, it was eventually proven, I think, by a blind mathematician that this was possible, like only about 50 years ago. But that was a very tricky thing with this pretty complicated differential equation. That fact is hidden in this differential equation. So you have solution techniques for solving the actual problem, and then you have actual other theorems about what the solutions could possibly look like. Okay, and so minimal surfaces are a very complicated differential equation that has some very nice properties that people have teased out, amongst which is Plateau's rules, amongst which is that there's a minimum curvature that can occur when you pull 2 soap bubbles apart. In other words, but I can get back to that a little bit later. And the reason I know about this is I've tried to apply some of the theory that was known to the field equations where we don't understand what's going on, the Einstein field equations where we don't understand what's going on. So, but for now, this is just an example of how to label the equation. Second order, you have 2 derivatives, that's what that refers to. Quasi-linear stands for the fact that it's linear in the highest order derivative, but it's got other messes, sort of second derivatives, quadratic over here in front of that. So that's quasi-linear. Linear is if it's just all the derivatives are just linear. Okay, quasi-linear is if it's linear in the highest order derivative, but not in the other ones. Okay, and then another guy that we're going to actually end the course with is the Korteweg de Vries equation. So this is an equation that has solitons in it. So it's a third order equation. So the third derivative is here. It describes water waves, and it's this unique thing that was discovered by Russell when he was looking at basically they had this barge where they had this lock system, and they had a whole bunch of water collected in the lock system. And it was like in 1880. And what they have to do is, it's the way they lift the ships up. So they basically put the ship in this little box, they pump the water in, and then the ship goes up, and then it flows away, it goes away at a higher level than what the previous river was. But then before the next ship comes, they pull up the gate at the back and let this little bit of water out, so that the next ship can come in and then pump the water in. And when they pull this thing out, the guy that was watching it thought, the water's just going to dissipate. And it didn't. This hump of water carried on, and he still writes to the journal. He was on a horse, and so he followed the horse. This hump of water with his horse along the canal, and he writes down it was like 3 or 4 miles, and the horse really had to move to keep up with the water. And he says, it was just surprising that this water mass didn't just go fall splat. And then he did a number of experiments just trying to reproduce that, discovered some of the properties, realized that the speed with which the wave went was dependent on how high it is, the waves stay together. And then much later, people actually looked at the equation and found a unique method of solution, unique properties that are not found in linear equations. It's once again non-linearity that's coming in here that's actually making some very strange things. And we're going to end the course with that because it's not included in most courses in PDEs, but it's very, very interesting. It gives you an idea of future research that can happen. Okay, so the general definition, a partial differential equation is an equation for a function which depends on more than one independent variable. And for example, the PDE may involve the independent variables, the function, and the partial derivatives of the function. Okay, so that's the most general definition we have. And so what we're going to do now is we're going to give the definition, We're going to state the problem, and then we're going to look at all sorts of solution techniques. So, for example, an PDE of order 1 is, you can write like this, okay? It's any function g of your independent variables x and y. The function itself, there's u implicitly of x and y, and the first derivative of u with respect to x of x and y, and the first derivative of u with respect to y, x and y, and order 1, so you only have first derivatives. Okay, so that's simply the definition of the PDE. You're given this expression, like we've been looking at the previous slides, or I can equivalently write it like this, and what you must now do is find u of x and y so that this whole thing is satisfied. Okay, a PDE of order 2, we often write like this, simply a function of x and y, u, its first derivatives, and all the possible second derivatives, and that must be 0. So this is just the formal definition, and generally the order of the PDE is the highest order derivative that occurs in the problem. So, for example, the minimal surface, the order is 2. That equation with the Laplace squared, the order would be 4. Okay, and now when we talk about solving this equation, it basically means finding a function that takes the independent variables to the actual function, such that when the derivatives of this function are taken, the combination satisfies the equation above. Right. So not very in depth, but it's important because the techniques we're going to use are quite abstract, and so when we say we've solved the problem, this is what we mean. Okay, so let's look at the first solutions. Here's our simplest problem that we had. Okay, we solve ux equals to 0 with u of x and y. Okay, and so this part is important because it actually gives us the information about what kind of solutions we have. So suppose we had, it was an ODE and we had u as a function only of x. Ux equals to 0 would immediately imply that u is a constant. Okay, so if we are told that u is a function of x and y, then u is the solution is that u is a constant, but a constant only with respect to x. Okay, it can still have an arbitrary function y. Okay, so the solution of this statement is simply u is a function of y. Similarly, let's solve vxx is equal to 0, where v is a function of x and y, and what we can do then is we simply make the problem simpler. We first let u equals to vx, okay, and then we have u equals to vx is a function of y only, and there now we must integrate it once more, and what we get is that v is the integral of this thing, which is effectively constant with respect to x, plus another arbitrary constant that's a function of y. Okay, so what we're basically doing is, for these examples, we're replacing, wherever we have a constant, we must remember it's a constant only with respect to the variable we are integrating with, and that it can arbitrarily depend on the other variable as well. Okay, so functions phi and f are arbitrary functions. And let's now go about and solve this equation. So we have wyx is equals to 0, and we know that w is a function of x and y. And so we once again put wy equals to u. So we have that wy is equals to phi y. And then we integrate it. Okay, so we basically integrate this with respect to y, so we get this integral plus an arbitrary function of x, okay, because we integrated with respect to y, but this thing was an arbitrary function to start with, so we might as well just say it's a function g of y plus f of x, where g and f are arbitrary. Okay, so the next one is, let's solve, just to show you what happens if we add one more unknown over here. So suppose we solve ux where u is a function of x, y, and z rather than just x and y, and you can basically guess the answer. We have that u is now a function of phi of y and z, where phi is an arbitrary function. Okay, so what the nature of what you know about the dependent variables of the function actually influences what you get out. And these examples are elementary, but the idea generalizes. Okay, so it's just where you would have worked with ODEs and added arbitrary constants, you are now adding arbitrary functions of all the variables except the one that you know explicitly its derivative is 0. Okay, so Vxx equals to 0. It's very similar to this example, except that the arbitrary functions are phi of y and z, f of y and z, and there we have it. Now solve yx equals to 0, where w of yx equals to 0, where w is a function of x, y, and z, and you can once again go through exactly this argument, and you can show that w is a function g of y and z, and f of x and z. Okay. And so you can look at this and make a more general observation. General solutions to PDEs in Rn, so that's the dimensionality. So an ODE is R1, these guys over here are R2, these guys over here are R3. Okay, basically have several arbitrary functions of n minus 1 variables. Okay, and here, how do we choose these functions? I'll show you several examples in what's coming. Is basically these arbitrary functions are then fixed by the boundary conditions. Okay, so remember when we solved an ODE, you could find, or you integrated an equation, you got the general solution plus a constant. But if you were integrating it between boundaries, then that actually fixed the constant. Okay, exactly the same thing happens on ODEs. It's just slightly more complicated because you're now no longer dealing just with point boundaries, but actually curves around the thing. Okay, but the idea generalizes. Okay, so let's have a look just also per introduction at the Laplace equation. So here we have Laplace equation. We're going to solve it in R2. So therefore we know that ux and u is a function of, say, x and y. And what I want to do also is just show you how this is actually related to complex analysis, because there's a very close connection between complex analysis and solving partial differential equations, and between solving partial differential equations and classical mechanics, because the two developed at the same time. In fact, many of the theorems, the people that worked on classical mechanics worked on quantum mechanics as well, and they understood the structure of differential equations and also used the structures they got from classical mechanics to push further the mathematics they were developing. So remember, and we will be using some results from complex analysis actually in finding solutions. So I just sort of want to remind you here at the start, or if you haven't seen it, is what the terminology means. F of x is known to be holomorphic if the Cauchy-Riemann conditions, in other words, f's partial derivative with the complex number z is 0. Okay? And remember, this equation, it's a complex function there, it's a complex variable, is the same. I'm now going to write it out. So here's my z's my complex variable, here's f, the complex function f. It's simply u of x and y plus I v of x and y. And the condition, the Cauchy-Riemann conditions, if you actually write out the full derivative with respect to z, remember that's a half dx plus I dy, and you apply it to f, okay, then what you get is the Cauchy-Riemann equations, and you get a first order system that's the same as the statement, and the first order system are simply these guys. Okay, so you simply apply this operator dz bar to f over there. You group the real and the imaginary part, and then you get that the real part is just dxu minus dyv, and dxv plus dyu. Okay. So these are the Cauchy-Riemann conditions. And this is an example of a system of first-order equations. So you actually now have two dependent variables u and v, two independent variables x and y, and you want to solve these guys together. And so what you can do is you can try and get rid of, in fact, this system makes it possible, you can try and get rid of one of the dependent variables by taking the derivative of with respect to x of the first equation, and you add the derivative with respect to y of the second equation. So you simply have partial xxu minus partial xyv, and you add partial xyv, so that one cancels with this one's derivatives, plus partial yyu. And what you then get is that, and that's equals to 0. So the Cauchy-Riemann conditions in complex analysis simply directly implies that the real part satisfies Laplace's equation. Okay, so it's one of the places where Laplace equation naturally arises. And then you can do the same thing, except that you now can subtract it and try and get rid of u, and you get that the Laplace equation of v is equals to 0. Okay, so it's just an example of where the Laplace equations comes from. It's also an example of that these guys, these first order system is exactly equivalent of two dependent variables, exactly equivalent to solving the second order system for one variable. And it's been a dance. Sometimes it's easier to solve this problem. Other times it's easier to actually use the fact that you know things about complex analysis to write down answers for this problem. And we're actually going to do both. We're going to use complex analysis to solve this problem, and then we're going to use other techniques to solve it as well, and we're going to show you how the two are together. And you should always get the same answer. So you can eventually use the one method to check the other methods. Okay, one thing that's particularly interesting over here, and it's probably a simple example, but it's got a lot of application when people do like all these animations. And the thing is, solving the system, or solving the Laplace equations, in fact, these two pairs, always results in what we call orthogonal equations. Okay, so what I mean, and that is often, and that's what that first picture was about. By orthogonal equations, I mean, is you get like your Cartesian grid, like x and y are always orthogonal on top of each other. But what it is now, what's also possible is that you can have a very strange shape, and you can have coordinates like polar coordinates, right? Polar coordinates also have circles going out and radial lines. And the circles and the lines are always at 90 degrees. So orthogonal basically means that your two types of coordinates cross at 90 degrees. And that's a very nice way to do it. So solving the Laplace equation with certain boundary conditions like this actually gives you a way of constructing orthogonal coordinates on any domain. Okay, so where it is used is when we try and solve fluid flow on incompressible fluids or irrotational flow. What we basically do is, suppose we want to know what waves look like if they're on a jetty. Okay, in other words, like waves in the ocean, the waves would come in, they would hit the boundary, and then they would reflect, and there would be a certain pattern that gets established. And to find out what that pattern is, we often solve Laplace's equations in certain boundary conditions. And so I haven't yet told you how to solve it. I'm just trying to tell you what the properties are to look forward to. So for example, if you have a complex function z to the n, okay, where n is equals to 3 over 2, then the lines of constant u and v are the blue lines and the cyan lines. So you can see they remain orthogonal. So if you wanted to solve Laplace's equation on a certain domain like this, you would actually get an exact analytic solution that you could actually work with. And the lines, the tubes, will always be orthogonal to each other. Another example, if n is equals to a half, then the real and imaginary parts would simply do this. They would be a bunch of parabolas that also intersect always at 90 degrees. And they would, like this type of problem, suppose, you know these weirs that you put out into the ocean? If, like the weir, suppose you're in the ocean and you've built this solid, like a fishing thing, okay, and it's like a fishing wall. If you look at the waves that come in, will basically hit the wall and then bend around it. So you're going to have one coordinate that corresponds exactly to the shape of the waves and the boundary on the weir, and then you're going to have this other coordinate that just compensates. Okay, and both of these are examples of solutions of Laplace's equation, because z to the n is always a complex solution to Laplace's equation. And these functions are basically the real imaginary parts. In other words, u and v. Let's suppose u is the dark blue and v is the light blue. And they are tremendously useful when you actually solve equations with the boundaries. Okay. I haven't yet told you how to solve it. I haven't yet used the technique. I'm just giving you an idea, as for the Afrikaans people say, it's toekomsmusik, music of the future, of what is coming. And we're going to actually look at some of these coordinate systems, because you actually get special differential equations, and these are usually differential equations they solve in physics that are separable. But what is interesting is you can actually classify all of them. There are not many of them. And you can actually work out which coordinate systems are possible and which they become separable in. Right. So what I'm going to do is I'm going to just take a little break for 5 minutes, that you can get your concentration back, and then we're going to go on to the second part, the advection equation. Let me just stop the recording.